Hi, my name is Dana Golden. Tonight we'll be doing SVM and tree-based models. So we've been talking for a little bit about classification. Um, Classification starts with exploratory analysis. You create histograms, box plots, group bar charts. As you can see here, then you can perform a variety of possible uh, models for classification. Logistic regression, obviously, is the workhorse in economics. It's a relatively simple model. We just optimizing a function that separates two classes using effectively a linear classifier, though not always, because sometimes you have polynomial logistic regression. Then you have decision tree, which is you sort based on particular values of a characteristic. You have support vector machines and random forest. Support vector machines creates lines in theoretical space to separate data. Random forest is like a decision tree, only it involves what's called boosting or bootstrap aggregating. And then you have k nearest neighbor, where you assign points to the points that were held by several of the closest points. And then you have naive Bayes, which is a very old Bayesian classifier. And then if you want to evaluate this, you can use confusion matrix, and you can use ROC and AUC. So support vector machines is an important algorithm for classifying. It's always been very popular in the machine learning community. And the goal is to find a hyperplane in n-dimensional space that separates two classes. It's valuable because it provides a more versatile way classifying high-dimensional spaces, but it's computationally and memory intensive to run. So this is some examples of the decision boundary you get with support vector machines. And you can do it with either a linear kernel or a non-linear kernel. So what happens when you do it with a linear kernel is you simply find lines in n-dimensional space that separate the different points in different classes. When you have a non-dimensional kernel, though, you don't necessarily have to find a line, because you change the measuring system. You change the measuring system. You make a transformation, and so you can measure with an RBF kernel, which is radial basis or a normal distribution. And then you can use a polynomial, and you can learn much more complex classifiers in three-dimensional space. So at its base level, it's very similar to logistic regression, but because you're able to transform to much more complex bases, you're able to learn a lot more separating lines. So how does SVM decide how to draw these lines? So SVM finds the margin that maximizes the distance between the closest data points from both classes. So this is the distance between the hyperplane and the observations closest to the hyperplane of support vectors. So you're looking at, you have these this margin here, this line here, and you have these points that are close to it, and you're trying to maximize the distance from those points to the line. So SVM finds the weight and bias that maximize the margin. It's very similar to perceptron. Effectively, at one level, it's effectively the same as a perceptron. And then when you add a more layers, a neural network becomes more distinguished. But effectively, you can think of it as base as a perceptron that can classify in a very much more general way because it can take on so many more possible data types. Yeah. So what if there's a nonlinear boundary? And this is what makes SVM so special. You transform the data in the space of the type of the boundary to make boundary linear in that space. So there's input space that's, there's this nonlinear boundary, and then you transport the data into the feature space, and now you can deal effectively with that nonlinear boundary. So one of the things that I think surprised a lot of people, given how popular and how powerful this algorithm is that SVM is not naturally designed to deal with multiple classes. So two possibilities for dealing with multiple classes in SVM. The first is 1V rest. And this means you perform SVM iteratively between one class and each of the others, and you take the class where you're most confident in it. Just do one versus the rest, and then you find the class you're most confident in, and that's your classifier. You also do 1v1. So you do one class against each of the other possible classes, and you take the class with the most confidence. You can kind of see how this would be very computationally intensive. So SVM is also valuable for anomaly detection. So one class of SVM is a common algorithm to find the smallest radius ball that surrounds all data points. So all data points outside of the ball are considered anomalies. So you have this original data set, and maybe there are some anomalies in there, maybe there weren't, but you take that data set as the real data set, and everything outside of it is an anomaly. Another thing you can do is you can say, well, any data, so I'm going to find the smallest ball that can fit 90% of the data, and everything outside of that is an anomaly. And that's what you really have going on here. So that's one class SVM. We assume that there's normal data and there's anomalous data, and you try and separate the normal data from the anomalous data. So we move on to talk about CART, or classification regression trees. Classification regression trees separate classes or data points based on cutoffs and data. So classification trees separate classes based on the values of features that provide the most data. Majority classes taken the end. Regression trees are the same, but with averages. So when should you use decision trees? Linear regression outperforms decision trees when you have an average relationship. So if you have data that looks like this, where maybe it's a little bit noisy, but on average it's kind of linear, then linear regression outperforms. Once again, basically the idea here is that even if it's noisy, there's on average the same relationship follows through, or the relationship changes at a constant rate throughout, maybe in a quadratic form. But sometimes that doesn't hold. There are a lot of processes in the real world where you actually have jumps. So actually here, if you have a linear regression, you get something like that. Well, that's not what this process is. That's not what's really going on here. In actuality, what the process really is something like that. So in actuality, there's an asymptotic threshold. So when you have these discrete jumps in your data, when you have, it's not necessarily that there's a change with one value, but there's a big jump, that's when you have a really great value from decision trees. So I think a lot of economists kind of frown on decision trees, and they're like, well, it doesn't work better than linear regression for this reason and that. Actually, the two work very well when dealing with two very different types of data. And decision trees work really well when it really is about thresholds and you really do see kind of sea change. Particularly decision trees outperform when the relationship involves jumps or thresholds. A good example of a time when decision trees are very useful is in stock markets. Stock markets and survey data is somewhat useful. So with survey data, maybe you have characteristic one and then characteristic two, and this really quickly lets you sort through your sample size. That's one use. But another thing is if you're doing the stock markets, if any of you've ever taken finance classes, you'll know there are these things called binomial. There's the binomial asset processing model, which is basically the idea that if the asset is in this range, it's worth this much. In this range, it's worth this much, and the asset's worth more as it goes on. Something else kind of falls through for stocks. Sometimes you have a stock, and if it shows this behavior, you then want to check if it's also showing this behavior. And if it's showing this behavior, you also want to check if it's showing this behavior. And then if it is showing that behavior, you want to buy. I've actually created algorithms like that in the past, and they weren't useful enough to actually make money, but I think it's a useful exercise to think about trading as a decision tree. And, you can find some interesting places to start by doing that. So how do you judge where to put the splits? How do you decide how to split your data? So you use what's called an impurity measure. So you can use the Gini index, and this measures the probability that a random observation will be misclassified. You can also use entropy, and this focuses on the amount of randomness in the sample. It's minimized when all share one class and maximized when half the observations are from each class. So this is the idea of information gain. So if you have a data set, let's not do that. If you have a data set that's like this, can I change the color? I'd like to change the color to red, but I don't know that that's possible. Let's change the shape. Let's erase all my drawings, and then let's draw this, and then let's start with some circles. Circle, 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 circle. And then let's add some rectangles. So you want to, some rectangles over here. You want to find the boundary that best separates them, and you've gained the most information about your data set by adding this boundary. So that's what information gain really is you're decreasing the entropy. You're decreasing the amount of randomness in your data set by now having split up the data set. It's a pretty common thing in information theory, very common in natural language processing. Interestingly enough, if you work it out, logistic regression is a minimum entropy classifier. So in some ways, under certain conditions, a logistic regression is equivalent to a decision tree, though those conditions are pretty rare in real life. My introduction, most regression trees focus on variables that most reduce variance and either take the median or average or experiment with a range of values of the split. So you're trying to either reduce the variance or reduce the entropy. And you prune to reduce overfitting by deciding to restrict the level of complexity or granularity of the tree. Basically, the idea is you don't want to learn a really complex tree, and at the end, you only have one observation at each node. You want basically a relatively simple tree, and you want a few observations at each node that are well separated, but not fully separated. If you have to fully separate, you might as well not do anything, because if you have to go all the way, that's just going to end up overfitting. It's going to cause more problems than it solves. So how to prune, how to choose a tree that is not too complex. You can choose a maximum depth. You can say the decision tree is only going to be 2 deep. You can choose a minimum number of samples per leaf. You can say, well, this has 20 samples per leaf, so we'll go on. This now has 5 and 5, and 10 and 15 and 5. So this one we're going to stop, and this one we're going to continue because we're going below 10. And then you can do minimum samples per split. You can say this one only has 20, and we don't split above 20. And you can choose maximum number of features, maximum. So this is another thing that I think is interesting with decision trees, is you can use feature 1, and then maybe there's still value in feature 1, so you split again on feature 1. So this would be restricting to a set number of features, even if you're using you're able to have substantially more depth, substantially more nodes. You can also do pruning after the tree is created. So pre-pruning is before the tree is created, setting boundaries for yourself in terms of what you're going to accept. Post-pruning is you want to remove the complexity. So here's a visualization of a classification tree. You have an outlook, is it sunny, is it going to rain? And then if it's Sunday, is it humid? If it's humidity is greater than 75, you predict yes. If the outlook is overcast, you predict that is yes. I think this is bring an umbrella. Should you bring an umbrella? Outlook sunny and humid, yes. Outlook sunny and humid with temperature greater than 75, no. Outlook windy, and then if it's forecast for rain and the outlook's windy, you predict no. Or you predict yeah, or windy is no, yeah. So bootstrapping is the final part of the lesson. When bootstrapping, you sample with replacement from the original data set. So you might have heard of this as bootstrap aggregating or bagging. Basically, bootstrapping increases the sample size and reduces bias by increasing variance, common in statistics and econometrics, particularly for finding standard errors. And a technique in machine learning that uses bootstrapping is random forest. Random forest generates decision trees using bootstrapping and randomly selects a subset of features. Random forest then builds a decision tree on a new data set and repeats for a set number of iterations. A majority vote decides which classes of any data, what the class of any data point will be, and in the case of regression, an average is taken. So you start off with a set number of data points. You create a decision or regression tree, classification regression tree, and then you sample from your data to create the regression tree. And then you do that over and over again. You create a bunch of different trees, and then you choose the average. The idea of a random forest is to think about the possible trees you could have gotten rather than just the one you did. So here's an instance of a random forest right here. You have 3 different trees, all using data randomly sampled from your original data set. And then each of them is predicting a class for your particular observation. And then now the majority votes, the majority of the trees vote on what class is, and that becomes the final class. So yeah, this the idea is to reduce the bias. So when to use random forest has higher variance but lower bias than decision trees. they're less likely to overfit with a few data points, but they're less interpretable as a single decision tree. I have always found that random forest is a great algorithm. It works out very well with data, but random forest can be more difficult to create and sensitive to board draws. So the final thing we're going to talk about tonight is boosting. So the idea of boosting is that one model might have a lot of bias in it, and there might be things you can learn from multiple models. So the idea of boosting is you take a set of simple models and rules and you create a stronger model. It works as individual models each learn different rules based on different data. In classification, the weighted majority rule taken in the regression, you take the weighted average. This is the idea of boosting. In one model, you learn this line. And so you say, these are all blue, these are all red. Well, not all of them are red. You have these three blue ones right here. This other model, you learn these two are red, this is red, and this is all blue. In this third model, you learn this line, and you say, all of this is blue, all of this is red. So you're learning different lines and you're learning different features of the data. So maybe this is one feature of the data. This is one thing about the data that you can learn. And this is another thing about the data you can learn. And this is another thing. And so you're combining all these models and you eventually get something that does a great job. So this one combines all three, takes a weighted average of all three classifiers. It has all three classifiers vote, and it says, well, should this be red or blue? Well, it's red in this model, it's red in this model, it's blue in this model, therefore it's red. And it actually, because each model is learning different information, it actually performs better than any of the individual models do on their own. Boosting only really works as an aggregation technique when you're learning different features and different data in each of your models. In boosting, multiple models are created focusing on different features of the data set. In bagging, a single model is trained using data sampled with replacement. So in boosting, multiple models sampling without replacement, bagging the same model but sampling with or sampling without replacement. Boosting is multiple models, while bagging is the same model but sampling with out replacements. So this is an algorithm called eta boost. For a set of n samples, you weight wi equals 1 over n. And then for m iterations, you fit a classifier k of x on all samples. You compute the error equals k, epsilon equals km times wi over wi. You compute alpha m, you update the weights, and you create new predictions. To show you how that works, this is the following data set. First coordinates represent the value of two features. The last coordinate is the label. So you start off with this data set. You have this solution. You learn this line, then you learn this line, then you learn this line. You find the weights, and you eventually end up with something that, while each line individually misclassified a bunch of points, all three of them together only misclassify 1 point. And now to finish off this lesson, it's going to be a very short lesson today. I'm going to talk a little bit about code, show you a little bit of code. So here I create a decision tree classifier with sklearn. So I load in the famous iris data set, create data X, and then Y as target. I do chain test split, create a decision tree classifier, fit it, predict the test set results, and then evaluate the classifier, and then visualize the decision tree. So let's see how this works. So I can't change the color. Command prompt, Python. And so creating a decision tree, fitting it, and then we plot the decision tree. It's separating based on petal width, petal length, and then it's basically making a prediction based on these basic features. And then we can also do the same with a random forest classifier. So we create the classifier, we train it, and then we predict the test data set. We create a confusion matrix and a classification report. And there we have it, confusion matrix. So this is a 3-class data set. So 19 were classified correctly of the first type, 13 the second, 13 the third. So all of the observations were classified correctly, which it should be because it's a very simple data set, and random forest is a relatively complex algorithm. So now this one, instead of a random forest, I'm going to show you SKM or SVM. We're going to put NumPy as MP. And then we create an SVM first from scratch. So this is SVM from scratch. It's just maximizing the margin between the data and the prediction. So let's first do that and then plot the decision boundary. So train the model, make predictions, and then determine the accuracy. So SVM is a very slow algorithm, but it works very well. Accuracy of 100%. Once again, very simple data set. And then let's look at that decision boundary right there. So look at that beautiful little boundary in space. Really nice how it's very simple. And you could obviously have a substantially more complex boundary than that. So now we can also do this with sklearn. So we do the same thing, but now we take a test set and train set, we feed it to svm.fit, we predict, and we create confusion matrix and classification report. And once again, this one didn't do quite as well as the other one. It's a different data set. Before, just now, we were training on just a random data set, and now we're training on the iris data set. It's not performing as well on the iris data set. Let's see what the decision boundary looks like here. And here, because we have 3 classes, we have a non-linear, or we have 3 decision boundaries, and this one's not linear. So it's a little bit, it's relatively linear, but it's a little bit nice. It's, you can see how it's separating the purples from the yellows from the greens, but it's not doing a perfect job here. And you can also do non-linear SVM. This is SVM with the radial basis kernel. So this will be a non-linear boundary that we create. And look at this. It's a little, you can see I finally figured out how to change color. No, I didn't. You can see that shifting, and it's doing a slightly better job. Obviously, there's a danger of overfitting, but it's doing a little bit better because we're allowing this non-linearity. So that was SVM, and that was tree models. Let's see. I had some other code I could show tonight. If anyone's interested, let's see if there's anything I find particularly interesting. Nothing particularly interesting here. I think I'm going to leave it here tonight. If you have any questions about the other code in here, I guess I'll go through analysis of email spam. So this is a something I created with the data in the folder that it has some spam data, and then it prepares the data, then uses a classification regression tree, a random forest model, and support vector machines to figure out whether or not data should be spam or not spam. So you can look through that. It's very simple stuff, just more applied. I hope you all have a great day.